Pluto, once considered an essential planet in our Sun's solar system, is now classified as a dwarf planet, yet it continues to capture the curiosity of astronomers. Recently, leading astrophysicists like Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight by suggesting that it might be on a potential collision course with Neptune. But how could this be possible, and what would the consequences be if such an event occurred? Is this just an intriguing astronomical anomaly, or is there more to this impending cosmic drama? Let's explore the potential outcomes of a Pluto-Neptune collision. Pluto, the former planet now classified as a dwarf planet, remains a subject of intense study due to its unusual orbit. Despite being reclassified, Pluto continues to intrigue scientists and the public alike. Recent research by prominent astrophysicists has revealed that Pluto's orbit is dangerously close to Neptune's, and experts like Tyson and Kaku have raised concerns about the possibility of a catastrophic collision between these two celestial bodies, which could pose a significant threat to Earth. But how can such an event even occur? Pluto's orbit around the Sun is unlike any other planets in our solar system, taking a remarkable 248 years to complete a single revolution. Since its discovery in 1930, it hasn't yet finished one full orbit. What makes Pluto's orbit especially fascinating is its elongated shape and the steep tilt of 17 degrees relative to the ecliptic plane. Unlike the nearly circular orbits of the major planets, Pluto's orbit is more eccentric and inclined, adding complexity to its trajectory. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's orbit. For about 20 years during each orbit, Pluto comes closer to the Sun than Neptune, challenging our expectations of their relative positions in the solar system. This raises the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational interactions between other planets. When Pluto's orbit was first assessed after its discovery, astronomers worked to understand its unique path, particularly compared to planets with orbits closer to the ecliptic plane. Pluto's steep tilt and elongated orbit seemed puzzling, and scientists were concerned about its potential collision with Neptune. However, further analysis revealed a remarkable solution. The gravitational interactions between Neptune, Pluto, and other planets create a delicate balance that stabilizes Pluto's orbit. This phenomenon, known as the three-body problem in space physics, describes how three celestial bodies like Pluto, Neptune, and the Sun interact gravitationally with one another. This interaction can predict the future positions and movements of the bodies involved. In Pluto's case, the gravitational effects of Neptune and the Sun ensure that while Pluto's orbit crosses Neptune's, the two bodies never collide. This is due to a phenomenon known as libration. When Pluto crosses Neptune's orbit, it is positioned at a 90 degrees angle to Neptune, ensuring that the two planets are never in close proximity. Another protective mechanism is resonance. When Pluto gets close to Neptune or any other large planet, it is arranged in such a way that it stays above or below the orbital plane of the other planets, adding an extra layer of safety. Moreover, the concept of chylation, studied by three scientists, Vonel, Kappas, and Lev, explains why Pluto's orbit remains so stable despite its apparent irregularity. This gravitational interaction causes Pluto's orbit to be remarkably predictable over billions of years, suggesting that the planet follows a specific pattern despite its eccentric orbit. Predicting astronomical events, especially involving complex orbits like Pluto's, presents significant challenges. The inherent unpredictability of such systems means that long-term forecasts are fraught with uncertainties. While mathematical models are crucial for understanding celestial movements, they depend heavily on the precision of initial conditions. Even small changes in these conditions can lead to vastly different outcomes, making precise predictions difficult. Despite the apparent stability of Pluto's orbit, the interactions between the giant planets offer valuable insights into the broader dynamics of the solar system. They reveal how the positions and gravitational forces of each planet can profoundly affect the behavior and stability of other objects within the system. So why are renowned astrophysicists like Neil deGrasse Tyson and Michio Kaku concerned about a possible Pluto-Neptune collision? Despite the many forces that prevent such an event, Tyson, a prominent figure in Pluto's reclassification, remains fascinated by the ongoing mysteries of our solar system. His commentary on Pluto's renaming and its complex orbital mechanics highlights the ever-evolving understanding of the planetary system, underscoring that while we know much, there is still much more to discover. This shift should not be seen as a downgrade, but rather as a significant refinement in how we understand the many bodies orbiting our Sun. Neil deGrasse Tyson's approach to the mechanics of the heavens revolves around continuous learning. He views the complexity of Pluto's orbit as evidence of the vast amounts still to be discovered about space. His work emphasizes that as we uncover more about the universe, new questions arise, prompting further investigation and refining our understanding. Michio Kaku, a renowned physicist and futurist, offers a different yet complementary perspective. Kaku is celebrated for his ability to connect complex scientific concepts with visionary ideas. He highlights the turbulent forces that shape our universe, stressing the importance of constant observation and advanced modeling to predict and comprehend astronomical events. Kaku believes that examining the interactions between celestial bodies is not just an academic exercise but has practical implications. He warns that events such as a potential Pluto-Neptune collision could have far-reaching consequences, from altering our understanding of the solar system to possibly necessitating future space interventions. Kaku's modern outlook suggests that the better we understand these cosmic forces, the more prepared we will be to navigate and mitigate significant space events. Both Tyson and Kaku emphasize that space is a realm of boundless discovery, and while our current understanding is important, it remains limited. A broad scientific consensus currently holds that Pluto's and Neptune's orbits will remain stable for the foreseeable future, thanks to their orbital resonance and other gravitational forces acting on them. Therefore, an immediate collision between Pluto and Neptune is deemed highly unlikely. However, the intricacies and potential disruptions in their orbital dynamics mean that astronomers must continue to monitor these bodies to better understand their long-term behavior and any potential risks they may pose. While the possibility of a Pluto-Neptune interaction remains largely speculative, it underscores the importance of ongoing research and observation in space science. Technological advancements, including more sophisticated telescopes and computational models, will help astronomers refine their simulations and predictions. This ensures that we remain ahead of the dynamic and ever-changing nature of our solar system. Tyson's perspective on Pluto's reclassification, coupled with Kaku's focus on the unpredictable nature of celestial mechanics, highlights the need for continuous investigation and a flexible understanding of our universe. The potential impact between Pluto and Neptune serves as a case study for the challenges and opportunities in space exploration, emphasizing the importance of effective scientific inquiry, cutting-edge technology, and a willingness to revise our understanding as new data emerges. Pluto continues to fascinate both scientists and space enthusiasts alike with its distant and enigmatic nature. While its status as a dwarf planet has long been debated, its orbit and unique characteristics continue to engage researchers. Recent developments have again brought Pluto into the spotlight, particularly with the possibility of a gravitational interaction between Pluto and Neptune garnering attention within the space community. With Tyson and Kaku highlighting this topic, discussions about a potential Pluto-Neptune collision are sure to spark further investigation and inquiry. Studying these mysterious celestial bodies holds the promise of uncovering new insights into the mechanics of our solar system. As we look deeper into space, the dynamic and unpredictable nature of our celestial environment underscores the need for vigilance and ongoing research. While the potential interaction between Pluto and Neptune remains an area of scientific interest, it is crucial to consider the broader context of space exploration and the methods used to study celestial bodies like Pluto. The discovery of potential risks, such as a Pluto-Neptune collision, serves as a reminder of the immense complexity and unpredictability inherent in the universe. This realization draws attention to the advanced tools and techniques used by space scientists and physicists to understand the movement of celestial bodies. For example, mathematical simulations allow researchers to model and predict the behavior of planets and dwarf planets over long periods, using input parameters like mass, speed, and distance to evaluate the stability of orbits like Pluto's. Such models are particularly valuable when studying objects with unusual orbits, like Pluto, whose path around the Sun is distinct from the other planets in the solar system. Gravitational interactions between celestial bodies are also a key factor in understanding the orbits of distant objects. While Pluto's orbit crosses Neptune's, the gravitational forces between them do not result in a collision, thanks to their orbital resonance. This resonance ensures that even when Pluto comes close to Neptune, their orbits remain stable. However, the influence of other planets like Jupiter, Saturn, and Uranus could potentially disturb this delicate balance over millions or even billions of years. These gradual shifts could lead to more significant changes. In addition to gravitational forces, the Sun's gravity plays a crucial role in shaping the orbits of objects in the outer solar system. However, because Pluto is so far from the Sun, its gravitational pull is much weaker than that experienced by the inner planets. This means that Pluto's orbit is more susceptible to external influences. For instance, changes in the Sun's energy output over time could affect the behavior of objects in the Kuiper belt, where Pluto resides. These subtle variations could impact the long-term stability of Pluto's orbit. The study of Pluto's trajectory and its interactions with other celestial bodies highlights the complexity and ever-evolving nature of space exploration, reminding us of the need for continuous observation and advanced modeling techniques to deepen our understanding of the universe. Climate research also provides valuable insights into the outer reaches of our solar system. Pluto resides in the Kuiper belt, a region populated by numerous small icy bodies and dwarf planets. As astronomers continue to gather data through space missions, such as NASA's New Horizons, which conducted a flyby of Pluto in 2015, our understanding of this distant area is improving. New Horizons provided stunning close-up images of Pluto and its moons, revealing a complex world of icy mountains, vast plains, and unusual atmospheric phenomena. These findings are raising new questions about the formation and evolution of the outer solar system. As we continue to refine our understanding of Pluto and its relationship with Neptune, we must also consider the broader implications for space exploration and future discoveries. Studying distant objects like Pluto helps us gain a better understanding of the history of our solar system and the forces that shape planetary bodies. Additionally, these discoveries have practical applications for future space missions and human exploration. With ongoing technological advancements, our ability to monitor and explore the outer solar system is expanding, opening up new frontiers for discovery. While the likelihood of a collision between Pluto and Neptune remains extremely low, the fact that this scenario captures the imagination of scientists and the public alike highlights the continued fascination with the mysteries of space. The complexity of Pluto's orbit, the forces that shape it, and its interactions with other objects in the solar system remind us of the vast and unpredictable nature of the universe. As we continue to study these distant worlds, our understanding of the solar system will grow, revealing new insights and raising new questions. The potential for discoveries in the case of Pluto and Neptune is just one example of the many wonders of space that continue to captivate us, pushing us to expand the limits of our knowledge and explore the unknown. The ongoing investigation of Pluto and its orbit is likely to remain a key area of research in planetary science, as scientists seek to unravel the mysteries of this distant dwarf planet and its place in our vast universe. Although the possibility of a catastrophic collision with Neptune remains highly unlikely, the potential for further discoveries and insights into the dynamics of the solar system makes the study of Pluto all the more fascinating. As we continue to enhance our understanding of the outer solar system, Pluto remains an intriguing subject for both theoretical astronomy and practical space exploration. One area of ongoing research is the role of gravitational interactions between distant celestial bodies and their effect on the orbits of objects in the Kuiper belt, the region where Pluto resides. This belt, which extends beyond Neptune's orbit, is filled with a vast array of icy bodies, dwarf planets, and comets. These objects have remained relatively stable for billions of years, but their orbits can be disrupted by the gravitational forces exerted by the larger planets, particularly Jupiter and Neptune. Understanding how these interactions might alter the orbits of bodies like Pluto is an important subject of research. Recent studies have also explored the possibility that the solar system might have been very different in its early history. During this time, the gravitational influence of giant planets like Jupiter and Saturn could have scattered smaller bodies into the Kuiper belt, reshaping the current arrangement of objects like Pluto. This hypothesis, known as the grand tack theory, suggests that the outward migration of Jupiter and Saturn may have sent protoplanets racing through the outer solar system, altering the positions of smaller bodies like Pluto and Neptune. This reshuffling of the solar system structure may help explain some of the orbital anomalies we observe today. In addition to these gravitational factors, Pluto's atmospheric conditions remain an area of great interest. Pluto's tenuous atmosphere, primarily composed of nitrogen, methane, and carbon monoxide, undergoes dramatic seasonal changes as the dwarf planet orbits the Sun. The changing atmospheric pressure and temperature cause the atmosphere to expand and contract, providing a fascinating example of how distant celestial bodies interact with their environment. NASA's New Horizons mission provided crucial data, revealing that Pluto's surface is much more geologically diverse than previously thought, with mountain ranges, flowing ice, and vast plains, indicating a complex history of geological activity and atmospheric interaction. The study of these distant worlds, including Pluto, challenges our understanding of planetary development, evolution, and stability. As we refine our models and technology, new discoveries will likely continue to reshape our view of the solar system's past, present, and future.